Swayam Prabha. Digital India. Educated India.
In the last lecture, we discussed how energy methods can be used to formulate the governing equations for a beam. We started with the definition of strain energy and work potential, constructed potential energy, took its variation, and also saw how minimum potential energy can give to the weak form of the differential equation or the principle of virtual work, and that in turn leads to the boundary conditions and the differential equation, which is actually the force balance. The three ways of looking at static equilibrium, we saw it in the case of a beam, and we also said that that can be seen for the dynamic case as well. Today what we will do is we go to structural optimization of a beam. So, let us recap what we discussed in the last lecture, where we wrote potential energy here, where we have the strain energy and then the work potential. Work potential once again is the negative of the work done by external forces. Now, when we take this potential energy and take the first variation and equate it to 0 and do the integration by parts to get the differential equation. So, this is the differential equation, we write dE for it, differential equation, and we also have the boundary conditions as we write as BCs, boundary conditions. This is for a beam which has variable cross section, that is A is a function of x, x goes from x equal to 0 to x equal to L, and this is the cross section. At different values of x you have changing cross section, and for such a thing this is the differential equation and these are the boundary conditions. Okay. Now, let us go to the structural design problem. So, structural design problem. This is to say that variational methods or calculus of variations methods not only help us do analysis, which is this, we are analyzing the beam, finding its deformation and stresses and so forth. We can also do design. Okay. So, we can pose a problem which we had already done for bars, now we do for beams. Let us say I take the case of minimizing strain energy of a beam. We already have an expression for strain energy of a beam, we have done it for the bars. Actually, let us do that. Instead of strain energy, let us do another measure of stiffness. Minimizing strain energy is a measure of maximizing stiffness, is equivalent to maximizing stiffness. There are many other measures for stiffness. One of them is called mean compliance, we will call it MC, mean compliance, which is given by basically integral 0 to L of Q times W dx. Okay. That is basically saying that the work done by the applied force Q that is acting on the beam, right. So, if this is the beam is the neutral plane, so there is force Q of x acting, and that multiplied by the transverse displacement W is our objective function. So, work done by the external force, if that is minimized, it is called mean compliance. Mean in the sense that we can take this and divide by the length, that should be the mean, but dividing multiplying by a constant does not make much difference for an optimization problem. So, we do not actually put that, even though we say it is mean compliance. It is mean mainly because we are looking at the load and the work done by that load at every point in the domain 0 to L, and summing it up or integrating. That is why it is called mean. I can always divide by L, but that does not matter. Okay. This is basically work done by the external force that goes by MC, mean compliance. How do we minimize mean compliance? We want to define a variable which is area of cross section of the beam, A of x, just like we had done it for the bars. Okay. That is our design variable, subject to, as we had looked at the general framework for structure optimization problems, there are design variables which is in this case A of x, but you also have state variables which is this W. The state variable should be governed by differential equation. For a beam, the governing differential equation is right here, right. This is what we have already written, that is this one. So, let us write that. That is the governing equation, E I W double prime minus Q is equal to 0. That is the governing equation for the state variable W. When we want to minimize the mean compliance or maximize the stiffness, if we are given a lot of material, infinite amount of material, we can of course make any beam as stiff as it can be made, that is infinitely stiff, by making area of cross section infinity. But that is not allowed in practice. Beam theory itself will break down if we do that. But from practical consideration for optimization, when you want to minimize mean compliance or maximize stiffness, we should do so subject to the volume constraint. That is, we cannot have any amount of material that we want. We are given only, let us say, a certain amount of material V star that we will put less than or equal to 0. Nobody tells us at this time how much material to use, even though V star is given to us. V star may be given to us, but we may use only 50% of it. If we can find an optimum, we will be happy. That is why we put the less than or equal to there. Okay. And as we had said earlier, when you have a functional type constraint, which is this second constraint, we should put a Lagrange multiplier with an uppercase, because it is only a scalar, as opposed to a lambda x for a function type constraint. Again, let us recall, this is what we call global or functional type constraint, whereas this one, the first one, is local or function type constraint. Okay. This is an equality, this is an inequality, that is okay. We know how to deal with that using complementarity condition for the inequality. But let us understand the problem that we have a governing equation is a local or a function type constraint. We have resource constraint, which is a global or a functional type constraint. Let us also clearly write what is known to us, data. So, first of all, length of the beam is given to us, Young's modulus of the beam is given to us, and the loading Q of x is given to us, and the volume V star is given to us. Okay. Is this statement of the problem complete? Actually, it is not, because we have area of cross section as our design variable, but I find area of cross section over here, but I also find I. Is I known to us? It is not known. That is, I of x we do not know, but we can express it in terms of area of cross section by writing it as some alpha times A of x raised to some parameter beta, where alpha beta are numbers. How does it come about? Let us look at that. For different cross sections, this alpha beta will be different. So, we are writing here, I will rewrite it. We have I of x, we want to write as alpha times A raised to beta. Let us take rectangular cross section. Okay. Let us say the breadth is B and the depth is D. Okay. So, this D is depth of the beam, which is the dimension in the plane of deformation of the beam. If there is a beam that is deforming, the cross section will be deforming. There will be two dimensions for the cross section of rectangle. One will be in the plane of deformation, other is perpendicular. Depth is the dimension in the plane of deformation, and breadth is the dimension in the perpendicular direction for the beam. So, if my hand is a beam, when I am deflecting like this, right, this thickness is the depth, and this width that I see from the top is the breadth. Normally thickness, width, all those are confusing when you take beams that deform in plane versus out of plane and so forth. It is always good to use B for breadth, D for depth. Okay. Again, D is the dimension in the plane of deformation of the beam. Okay. So, if we have this, we all know that or many of you would definitely know is that this I, which is the second moment of area, is given by B d cube by 12, and area of cross section is given by B times d for this rectangular cross section. Okay. So, here if I want to write in this fashion, we can, right, that is to say in this case I, which is B d cube by 12, I can write as B d. Okay. It depends on what we assume as known, breadth or depth. To begin with, let us say that we assume that B is the variable whereas D is taken. So, I can write this I as B d cube by 12, right. So, if I want to put area, I need to multiply by B square and divide by B square. So, I can do well. Let us actually take D as the fixed value. So, I will take out D square, put 12 as it is, times B d. If I do this, essentially what I am saying is that this quantity here is my alpha, okay, because D I am assuming the depth of the beam and vary the width, okay, and beta that we have will be equal to 1, because it is just the area, B d is area, right. So, we get in the form that we wanted. Okay. Let us take that here. So, when we go back to the problem statement over there, let us assume that we know D, okay, and we know this alpha, which is, as we just did, is D square by 12 and then beta equal to 1. So, that when we take I in this form, I will have simply D square by 12 times A. So, in this particular case, I of x is D square by 12 into A. A is B d. So, I get B d cube by 12. This is by assuming the depth of the beam. Okay. On the other hand, if we want to make B assume, so if we assume B, right, then I can write I to be, we have B d cube by 12, I need to get area. So, I will multiply by B square and divide by B square. Then what do I get? I get 1 over 12 B square into A cube, because this particular thing is now B cube D cube, that is A cube. In this case, this becomes our alpha, this becomes our beta. Okay. Obviously, this way of doing it will be more difficult than assuming D and proceeding. We always, when we start, take something simpler. That is why I am taking D to be given, so that I can make the problem simpler, and later on we can consider B to be given and vary D. Okay. Now, taking this problem, the problem that we have, the statement that we have, let us encircle it. The problem that we want to solve is simply a calculus variation problem. Since we spent quite a bit of time in understanding calculus variations, we should be able to solve any problem that is given to us when a problem statement is complete, meaning that everything is properly written up. Then any number of constraints, whether equality, inequality, local or global, does not really matter. We can just mechanically do the variation, write the differential equation, boundary conditions, and formulate the equations, which when we solve the problem of structural optimization. Okay. Again I want to remind you that we had done this for bars, now we are doing for beams. Okay. Now, the first step that we do when we solve an optimization problem is to write the Lagrangian. So, the Lagrangian here we have the mean compliance, which is the objective function 0 to L q w dx, and then we have two constraints. One is a local constraint whose Lagrange multiplier is lambda, and we have to multiply that with the constraint itself, which is E I w double prime minus q. Okay. Again, if you want to look back, you can see what we have written. We have written this constraint and multiplied by Lagrange multiplier lambda. Similarly, we have to do for the global constraint where the multiplier is capital lambda. So, capital lambda into a, okay, because that is what is under the integral sign here, a dx. So, all of this multiplied by dx, and then we have lambda v star, that is just a constant, where when you are minimizing a constant such as this does not matter. So, basically that v star lambda times v star will be there. Okay. These are Lagrangian. So, what do we do? As we had done these steps, we have to remember as we are doing simple problems, bar and then now the beam. So, first thing we do is we take the Lagrangian variation with respect to the design variable, which is a here, okay, which we have to equate it to 0. If we do that, we get design equation. Okay. And if we do this for state variable equated to 0, we get adjoint equation. Okay. And when we take this, there are basically two variables, state variable and the design variable. So, we do not need to take variation anymore, but we have the governing equation. When I am writing the necessary conditions now, we have the governing equation, which is E I w double prime, which will simplify, because if you see this I here, we wrote it as that alpha into a, where alpha is d square by 12. Okay. So, that is what we do, because otherwise we take variation a, we wonder what I is again, that is now alpha a. So, I can also replace this, calling it alpha a minus q equal to 0, that is our equilibrium equation. And then we have the complementarity condition for the constraint that we have, which is the inequality 0 to L a dx minus v star, okay, is equal to 0, and we have this lambda greater than or equal to 0. Basically, these are what we have here are basically equivalent of KKT conditions, Karush-Kuntakar conditions. I must say these are equivalent, because the same arguments are applicable here. Those are what we have. So, again we should always count the number of unknowns and equations to see if we have enough equations to solve for those unknowns. The unknowns are, we do not know a of x, that is our design variable. We also do not know w of x, we do not know lambda x, and we do not know this uppercase lambda over here. Okay. So, when you have this, in fact, if you look at the data, you have to check, you look at all the variables that are in the problem statement and then see what in the data, whatever is not in the data, we should say that that is our design variable. So, here I am saying a is a design variable, right, that is an unknown. So, we list it in the unknown part, and then lambda we do not know, capital lambda we do not know, and w we do not know. Everything else we know here. So, that check will always be useful. Okay. Now, once we have these, we can write and see we have written the equations, design equation, adjoint equation, equilibrium equation, and the complementarity condition, and the condition that lambda should be greater than or equal to 0. Once we have these, we can proceed and solve the problem. So, we have 4 variables and we have 4 equations. If we can number 1, 2, 3 and 4. Now, let us look at the equation again. The Lagrangian is given here. This dx is extra because we already have the dx over there. So, qw plus all this Lagrangian, let us write the design equation. Before that, we need to expand this term. Okay. Let me do that. We are now solving in detail. So, that E I w double prime minus q will first substitute for E for I, which is alpha times A w double prime minus q. So, let me expand it once. E alpha into A prime w double prime plus E alpha A into w triple prime, and then one more prime. We have done differentiation once, q remains as it is. One more time, it will give us, I think it is safe to take E alpha outside, that will there in all of them. We have A double prime, I am taking derivative of this now, A double prime w double prime plus A prime w triple prime, that I am going to put 2 here because when I take derivative of this I get A prime w triple prime product rule, and then A into w fourth derivative minus q. Okay. Having written that, now let us write the Lagrangian one more time. Lagrangian, which is 0 to L q w plus E alpha lambda, because lambda was multiplying this thing over there, times A double prime w double prime plus 2 A prime w triple prime plus A w fourth derivative, and then we also had the uppercase lambda times all of this times, okay, let me use a different bracket because we already have that bracket. Let me use this curly bracket, dx minus lambda v star. Okay. For the design equation, we have to take variation of the Lagrangian with respect to A and equate it to 0. So, we have to write Euler-Lagrange equation by taking the variation of the Lagrangian with respect to A. So, we look for things basically, if I call this whole thing as my integrand f, then I have to write dou f by dou A. A is there, okay, A is here, we also have A is also here, and we also have A prime here, and we have A double prime here. So, I have to write dou f by dou A times dou f by dou A prime plus dou f by dou A double prime equal to 0. So, it is a good exercise for Euler-Lagrange equations application. So, we have this, right. So, based on this we can write the terms dou f by dou A is in 2 places. One is this E alpha lambda into w fourth derivative, that is what is multiplying A, and then we also have uppercase lambda, okay, that is the first portion. So, that is that. Let us use color coding. Second one, okay, that is minus A prime, there is E alpha lambda to w triple prime, that is dou f by dou a prime, and all of this we should take one derivative. Okay. And then we have this thing which is plus a double prime, that is E alpha lambda w double prime, and then 2 primes, 2 derivatives of that equal to 0. Okay. Let us simplify it a little bit here. So, we have this one, there is nothing to simplify, E alpha lambda w fourth derivative plus this lambda, this red one. Okay. It may be a good idea to leave it alone, because the fourth term will have something coming there. So, I will just put this as minus 2 E alpha lambda w triple prime prime, and then let us go to this last one. Let us take one derivative of this, that will give us E alpha lambda prime w double prime plus E alpha lambda into w triple prime equal to 0. Okay. Because lambda is also function of x. Now, we see that this thing here is also here, this is minus, this is plus, I can cancel up this 2 and this term altogether. Okay. So, one of these gets cancelled. So, we have a little bit simplified. Let us proceed to further simplification by 4 plus lambda minus 1 will have, okay, that is E alpha lambda triple prime. Let us expand it now, that will be E alpha lambda prime w triple prime minus E alpha lambda w fourth derivative. We are happy because this, the first term and this get cancelled. Okay. And then we have this the last term, which will give us E alpha lambda double prime w double prime plus E alpha lambda prime w triple prime equal to 0. Again, it is a happy situation because we see that and that cancelling. So, what we get with this is just this lambda, and then we have plus E alpha lambda double prime w double prime equal to 0. Let us keep it aside for now, because we do not know what lambda is as yet. So, then we proceed to do this variation of the Lagrangian with respect to w. Okay. So, that is over there. Okay. For us to write, I think we have to rewrite this Lagrangian down here, so that we can easily take the variation. So, instead of writing the whole Lagrangian, let me just write the integrand of the Lagrangian in that thing. So, I will just write f, okay, that is qw plus lambda times there was a fourth derivative, right. So, E alpha lambda, okay, qw plus E alpha lambda into A double prime w double prime plus 2 A prime w triple prime plus A w fourth derivative plus lambda A, that is integrand. So, once we have it, when we write the variation of the Lagrangian with respect to w equate to 0, our Euler-Lagrange equations, it will be dou f by dou w, we have that term here, minus dou f by dou w prime that is not there, w prime is not there, plus we have dou f by dou w double prime, we have double prime here. We also have triple prime and fourth prime. So, it is a very good exercise for calculus of variations problems. Triple prime plus dou f by dou fourth derivative and you have to take 4 derivatives there. That should be equal to 0. Okay. Let us do that, even though it may look intimidating, I think, but we can, this is a routine process. Dou f by dou w will give us q here minus w prime term is not there, that is 0, plus w double prime is there, that is going to give us E alpha lambda into A double prime and then double prime minus triple prime, we have E alpha lambda with a 2 into A prime, and then that goes as triple prime, and then we have E alpha lambda into A, and that goes to 4th derivative, that is equal to 0. Okay. So, w there is only q, w prime is not there, w double prime we have this term which we have, w triple prime we have this term, w 4th derivative we have that, okay, and E alpha lambda is there for all of them. Now, we need to simplify it. Okay. That simplification I would urge you to do it on your own. Simplification, it is just algebra, like we had done, many terms get cancelled. In fact, you would see that this adjoint equation, that is what we get when we take Lagrangian variation with respect to the state variable adjoint equation. Upon simplification, okay, in this problem adjoint equation will look as always like the equilibrium equation. Okay. This is a lengthy simplification, you can do it in a few minutes. If you do that, it is going to look like this. It is going to look as E alpha A into lambda double prime plus q equal to 0. Okay. This is how it is going to look like. If you compare it with the governing equation, which is this E alpha A w double prime minus q, here it is just the plus sign E alpha A w double prime. So, comparing these two, we can conclude that lambda equal to minus w. Okay. There is a minus q, here is a plus q. Once you know lambda equal to minus w, we go back to this equation and then find something. If I do this, it will become E alpha w double prime square equal to 0, because lambda equal to minus w. So, lambda double prime equal to minus w double prime. So, we get this. Now, what we get here again is that lambda is equal to E alpha w double prime square. What does it mean? Lambda E alpha are constant. So, w double prime should be constant. That means that it is not a function of x. So, w double prime, as we know, is strain, it is a function, but here it is a constant, and that is strain, and hence multiplied by E, that you will get stress, that is constant. So, this is exactly the conclusion we had arrived at in the case of bars, that if you want to make the structure the stiffest for given amount of material, then the strain or stress are uniform throughout the beam, meaning they are not functions of x. And once you know this, you have enough equations to solve, just like in the bar, which we will consider in the next lecture.